A man with no engineering degree designed a bridge across the widest navigable river in North America, using a material that had never been tested at scale. Every structural element was invented specifically for that one project. The Eads Bridge, completed in 1874, was the longest arch bridge on Earth, the first major steel structure in American history, and a design so radical that the engineering establishment declared it physically impossible. Almost nobody outside St. Louis knows it exists. The standard story of American industrial ambition runs through New York, through Carnegie, through the Manhattan skyline. But the deeper story, the one where a single engineer rewrote the laws of what could be built, happened in the mud of the Mississippi. What reconstruction allows us to do for the first time is go below the waterline, into the pressurized chambers where the real work happened, 40 feet beneath the river's surface, in a world no photograph ever captured. His name was James Buchanan Eads, and he had no formal training of any kind. He taught himself engineering by reading textbooks borrowed from a St. Louis bookstore owner who allowed him to study in exchange for sweeping the shop each morning. But Eads had something that no professor could give him. He had been to the bottom of the Mississippi. For decades, he had operated salvage vessels on the river, personally descending in an early diving bell to recover sunken cargo from the riverbed. He was, as far as anyone can establish, one of the only people alive who had seen the Mississippi's floor with his own eyes. He knew its texture, its geology, and the way its sediment moved under pressure. He knew it the way a surgeon knows a body. His public career began not with bridges, but with war. In 1861, the Union Navy needed ironclad gunboats for the western rivers. Eads designed and built a fleet of 7 in exactly 100 days, an industrial achievement that made him a nationally known figure. By 1866, he was standing on the St. Louis levee with a bridge proposal in his coat pocket that every established engineer in the country had already called delusional. Picture this: the Mississippi at that moment, 3/4 of a mile wide, fast and brown, carrying uprooted trees and the wreckage of steamboats, and a self-taught man preparing to cross it with steel. The man who would design the most technically advanced bridge in the world had never designed a bridge before. Think about what lies beneath that brown water. Not rock, not clay, but roughly 100 to 136 feet of loose alluvial sediment, sand and gravel and silt deposited over thousands of years before reaching solid bedrock. It shifts under load. It scours around obstacles. It compresses unpredictably and swallows anything placed on it without anchor. Eads specified that every pier for his bridge must reach bedrock, not rest on the sediment, not be driven into it, reach, through all of it, to the rock below. Every competing engineer, including the head of the Army Corps of Engineers, publicly declared this condition lethal and mechanically unfeasible. The Army Corps submitted an official report recommending the bridge not be built as Eads designed it. Eads traveled to Washington personally and lobbied Congress until the report was overruled. He did not modify his design. He overruled the experts instead. The only prior use of compressed air caissons at comparable depth had been in European construction. The deepest anyone had gone was roughly 60 feet. Eads was proposing to nearly double the known limit of the technology. The thing that makes the Eads Bridge stand today was also the thing every expert authority said would destroy the workforce before it could be finished. To reach bedrock through that column of sediment, Eads designed a pressurized wooden chamber the size of a house, sealed and sunk alive into the river floor. Each caisson was built from timber and iron, with walls nearly 4 feet thick. Compressed air was pumped inside at pressures up to 45 pounds per square inch, nearly 3 times normal atmospheric pressure, to hold the river water back while workers excavated the mud below. Step inside. The airlock door seals behind you, and your ears pop sharply as the pressure climbs. The ceiling is 9 feet overhead. gas lamps throw orange light across 70 feet of low, flat space. The floor is river mud. Above you, through 4 feet of timber, the Mississippi presses down. The hiss of compressed air never stops. The interior working space was roughly 75 feet long, 60 feet wide, and 9 feet high. Dozens of men worked simultaneously in artificial light, shoveling mud and broken rock into buckets that were lifted out through an airlock above. The work was measured in inches per day. As excavation progressed, the caisson, weighing thousands of tons, slowly sank under the weight of the masonry pier being built on top of it. It descended through the riverbed a few inches at a time, guided by the hands of men who could hear the river through the ceiling. As workers ascended from these high-pressure chambers back to normal atmospheric conditions, many experienced severe joint pain and, in the worst cases, sudden paralysis. The condition had no name yet. Workers called it simply the bends, for the way it forced the body to double over. A St. Louis physician named Alphonse Jaminet was hired specifically to study it. His 1871 report was one of the first clinical analyses of what we now call decompression sickness. He observed that slower ascent appeared to reduce symptoms. The physiology of nitrogen in the blood would not be understood for another decade. At least 14 workers lost their lives during the foundation work. Many more were permanently disabled. Eads himself descended into the caissons repeatedly to inspect progress and suffered multiple severe episodes. At one point, he directed construction entirely by written correspondence from his bed. The physician Eads employed to protect his workers produced the first serious study of a condition that medicine would not know how to prevent for another 50 years. The human cost of the foundations stayed hidden beneath the waterline, while something harder and stranger was happening above it. Eads had specified the bridge's arches be built from chrome steel, an alloy that had been tested only in laboratory quantities and never produced in the volumes required for a structure of this scale. Close your eyes for a moment and consider what it means to build something from a material that American industry cannot yet manufacture. Eads was writing letters to Sheffield, England, rejecting steel that other engineers would have accepted because his calculations required specific strength tolerances and the tolerances would not negotiate. He held payment on entire shipments that failed. His proof tests. This caused a financial crisis that nearly halted construction. The steel subcontractors included associates of Andrew Carnegie, who objected to the rejection standards. Eads overruled them and held the line. Every tube installed in those arches had to withstand a load significantly in excess of its calculated working stress before it was allowed onto the bridge. This was not standard practice. It added months and money and produced a structure that was, by a wide margin, the most rigorously tested steel construction in American history. The bridge that exists today as the oldest major steel bridge in the United States was built from a material that the United States could not yet reliably produce. It proved the material worked before the industry existed to supply it at scale. With the foundations descending through the riverbed and the steel arriving from England in tested sections, the arches themselves now had to be assembled across a commercial navigation channel where no scaffolding could be placed in the water. Eads used the cantilever method. Each arch rib was built outward from both piers simultaneously. The two halves held in tension by temporary wire cables anchored overhead, growing toward each other across the open air above the river until the two halves met at the crown and locked into compression. The timing of that final closure was calculated to fractions of an inch. Imagine approaching from the river on a steamboat in August 1873. Two arms of steel reach toward each other across the sky, 50 feet above the water, held by cables. On the structure above, workers are packing ice around the steel ribs in the Missouri summer heat, waiting for the metal to contract by fractions of an inch. The entire Mississippi River traffic is watching. The arch closure had nearly failed. Thermal expansion from the summer heat had pushed the steel tubes apart. by enough that the two half-arches could not be brought together at the crown. Eads calculated the solution overnight. Pack the steel with ice to contract it. It was not in any engineering manual. It came from years of watching metal behave on salvage vessels in every season of weather. The most precise engineering operation in the bridge's construction, the closure of a 520-foot steel arch, was solved with a delivery of river ice. When the arch closed and the cables were released, the load transferred into compression exactly as calculated. The bridge was, for the first time, structurally complete, but it still had to prove itself to a public that had watched men suffer building it and was not confident it would hold. Think about what you would have seen from the St. Louis waterfront on July 4th, 1874. 3 steel arches spanning 3/4 of a mile of river, the longest clear span anyone alive had ever seen in steel, and 14 locomotives parked side by side on the deck, not moving, while engineers with instruments watched from the piers below. The load test was conducted in the days before the public opening. 14 locomotives were driven onto the structure simultaneously and stopped. Engineers measured deflection at each pier. The bridge moved less than the calculations had predicted. Crowds watched from the riverbanks. The original plan had been to use elephants. A widely held folk belief held that elephants instinctively refuse to walk onto unsafe structures. Eads rejected the idea on engineering grounds and substituted locomotives as a quantifiable load. The elephant belief was so persistent, however, that a circus promoter named W.C. Coop arranged a full parade of elephants across the bridge the following year, specifically to settle the question in the public mind. The most technically rigorous bridge test in American history was nearly replaced by a theory about elephant instincts. On the day of opening, an estimated 150,000 people came to St. Louis. President Ulysses S. Grant was in attendance. General William Tecumseh Sherman drove the ceremonial first spike. Sherman later wrote that crossing the bridge on foot felt like standing on the chest of a sleeping giant. "You know the force is there," he wrote, "and you know it is contained." The bridge did not move. The city declared itself the engineering capital of the continent. What happened next is the part of the story almost nobody tells. The Illinois and St. Louis Bridge Company went bankrupt within a year of the opening. Railroad interests that had opposed the bridge's construction succeeded in blocking through rail traffic for years, strangling the revenue model Eads had designed. The financial structure that built the bridge collapsed faster than any of its steel. Eads himself received almost nothing. His payment had been contractually tied to cost savings during construction, and those savings had been consumed entirely by the steel rejection program and the medical crisis in the caissons. He spent the last decade of his life in lawsuits with contractors and financiers over a structure that had proved everything he believed. When the bridge was threatened with demolition in the 1970s due to deferred maintenance, an engineering survey was conducted before any renovation work began. The chrome steel Eads had fought to source, tested, and installed 100 years earlier was still at full structural strength, no measurable corrosion in the sealed tube sections. The material Eads had been dismissed for specifying had simply refused to age. The bridge, built from a material that did not yet exist, is still working infrastructure today. The financial empire built to profit from it lasted 12 months. If you take a boat down the Mississippi past the St. Louis riverfront today, you can see the exact waterline on the piers where the caissons were sealed against the river mud 150 years ago. Below that line, the pressurized chambers are still there, still sealed, still holding the air that was pumped in, while men shoveled in the dark below the river floor. Nothing has moved. The river presses against them the same way it always has. The Eads Bridge now carries the St. Louis Metrolink light rail system. Commuters cross the Mississippi twice a day on arches assembled by workers packing ice in the Missouri heat, over foundations sunk by men who could hear the river through the ceiling. Most of them do not know this. Eads never built another bridge. He spent his final years fighting over the structure that proved everything he believed about steel and pressure and the limits of what was buildable. The river is still there. The bridge is still there. The men who shoveled in the dark are not.